The role of AI in transforming secure access service edge or SASE frameworks is really pivotal. It enhances threat detection capabilities, automates security policy enforcement, and optimizes network performance through real-time analytics and machine learning. This transformation enables organizations to respond more effectively to sophisticated cyber threats while at the same time improving the overall user experience. AI-powered threat detection represents a cornerstone capability in modern SASE frameworks, fundamentally transforming how organizations identify and respond to cybersecurity threats. Unlike traditional security approaches that rely on static rules and signatures, AI-driven systems continuously analyze network behavior to detect anomalies and potential threats in real time, automatically containing risks before they spread throughout the network. The integration of machine learning algorithms enables SASE platforms to analyze multiple dimensions of security data simultaneously, including web page source code, images, text, and URL patterns to detect potential threats with greater accuracy. This kind of multifaceted analysis significantly enhances phishing detection capabilities and protects against similar cybersecurity threats that might, evade conventional security measures. AI's contribution to threat detection within SASE frameworks includes several key capabilities. First, anomaly detection. AI continuously monitors network traffic patterns, identifying deviations from established baselines that may indicate compromise. And then, predictive threat intelligence through continuous learning and pattern recognition, AI can predict potential threats and implement preventive measures before attacks actually materialize. Behavioral analysis uses advanced algorithms to examine user and entity behavior, helping to spot suspicious activities that might hint at account compromise or even insider threats. Zero-day threat identification is another key benefit. AI can detect previously unknown threats by recognizing patterns that are similar to known malicious activities. This really helps address the critical challenge of zero-day vulnerabilities. The practical impact of these capabilities is honestly substantial. For instance, AI can identify polymorphic malware like a motet, which evades detection by changing its code structure, but still keeps its malicious intent. When suspicious activity is detected, AI-powered SASE solutions can automatically isolate potential threats, stopping lateral movement across the network while security teams investigate. AI not only enhances incident response through automation, but it also automates security policy enforcement by centralizing data from network and security events in a data lake. AI algorithms continuously learn and improve, providing actionable insights for faster decision-making. This approach in turn significantly reduces the time needed to identify and mitigate security incidents, helping to address the growing gap between the sophistication of attacks and traditional defense capabilities. The efficiency of AI in automating security policy enforcement can really relieve security teams from those tedious manual tasks, allowing them to focus on more strategic activities. As cyber threats in enterprise environments become, increasingly complex, AI-powered threat detection within SASE frameworks provides organizations with a way to manage this complexity without compromising performance or security. The technology continues to evolve toward deeper integration with zero-trust frameworks, supporting human judgment rather than replacing it, while helping people work and connect safely regardless of location. Machine learning, or ML, has truly revolutionized application discovery within SASE environments, enabling organizations to automatically identify, classify, and secure applications across their networks without relying on manual configuration. This capability addresses a critical challenge in SASE implementation, maintaining visibility and control over the expanding universe of applications that users access. So, traditional application discovery methods rely on predefined metadata or manual identification processes, which honestly can become outdated pretty quickly in today's dynamic digital landscape. On the other hand, ML-powered application discovery uses sophisticated algorithms to analyze network traffic patterns and automatically identify applications without needing any existing metadata. This approach employs techniques such as disconnected component and outlier detection, which help determine application boundaries by analyzing how virtual machines communicate with each other. The process actually works by examining network traffic flows to identify groups of systems that communicate more frequently with each other than with external systems. The ML algorithms can first automatically detect application boundaries based on communication patterns, and second, identify shared services used across multiple applications. These algorithms can determine application tiers by classifying systems with similar network behaviors. And also, they continuously update application maps as communication patterns evolve. For example, VMware's vRealize Network Insight Cloud utilizes machine learning to analyze network traffic from vSphere Distributed Switch or VMware NSX, automatically discovering application boundaries. The system can distinguish between dedicated applications and shared services, such as Active Directory or DNS, based on their communication patterns. Within each application boundary, the machine learning algorithms further classify systems into tiers, like web, application, and database, based on their network behavior and open ports. In the SASE context, this capability is particularly valuable as it enables security policies to be applied based on accurate current application mapping rather than outdated manual configurations. Palo Alto Networks has integrated a similar machine learning-based application discovery feature into its Prisma SASE offering, allowing the system to automatically identify new applications, assess their risk profiles, and adjust security policies in real time. The benefits extend beyond mere discovery. When machine learning identifies applications running on the network, it simultaneously reduces manual oversight requirements while ensuring that network and security policies remain current with the latest application landscape. This automation frees security teams to focus on higher value activities while maintaining more accurate security postures. Open Systems has implemented this approach in their unified SASE platform, where machine learning-based application discovery serves as a foundation for more intelligent security policy management. The system continuously learns from incoming traffic and historical patterns, enabling more precise application control and security policy enforcement across distributed environments. As organizations continue to adopt cloud-native architectures and SaaS applications, machine learning-powered application discovery becomes increasingly essential for maintaining visibility and control. The technology provides the foundation for other AI-powered SASE capabilities by establishing accurate application context for security policy decisions and performance optimization. So, digital twin technology is really revolutionizing how organizations test and optimize wide area network performance in software-defined access environments. By creating virtual replicas of physical network infrastructures, these digital twins allow for comprehensive testing without any disruption to production environments. They basically provide a secure sandbox where teams can evaluate performance under all sorts of conditions, before making any changes in real-world systems. At its core, a digital twin for WAN performance testing is essentially a virtual replica that stays synchronized with the physical network across time. It captures configuration, performance metrics, and even historical data. This approach lets security teams validate systems before they actually build or modify any physical infrastructure, which honestly can really improve production quality and reduce the risks that come with implementation. The testing process typically follows 4 key stages. First, there's data gathering, which involves capturing production data by attaching physical events to interfaces and synchronizing with live applications to record real-time data events. Next, we have data sequencing, where the captured events are exported and sequenced based on time and event ID, all to recreate accurate process flows. Digital replication involves creating a replica of the production environment where test applications maintain real-time synchronization with live systems. Performance testing uses this replicated environment to test network configurations, security policies, and application performance under, various conditions. The benefits of SASE implementations are substantial. Digital twins allow organizations to visualize products, analyze performance, and modify virtual environments before creating physical prototypes or implementing changes to production systems. This capability is honestly particularly valuable when testing how security policies might impact application performance across distributed networks or how network optimizations might affect security posture. Real-time monitoring capabilities further enhance the effectiveness of testing. Digital twins collect data from embedded sensors in physical network components, creating a continuous feedback loop that enables ongoing optimization. This approach allows security teams to anticipate potential failures, mitigate performance issues, and verify that SASE implementations will function as expected under real-world conditions. As SASE frameworks continue to evolve with AI integration, digital twin testing becomes increasingly important for ensuring that automated security policies don't negatively impact network performance. The comprehensive testing environment allows organizations to validate that AI-driven decisions align with business requirements before deployment, significantly reducing the risk of service disruptions while maintaining robust security postures. Behavioral analytics anomaly detection serves as a cornerstone capability within SASE frameworks, fundamentally enhancing security posture by identifying deviations from standard patterns that may indicate threats. Unlike traditional security approaches that rely on known signatures, behavioral analytics focuses on detecting unusual activities that diverge from established baselines, making it particularly effective against sophisticated and previously unknown threats. At its core, behavioral anomaly detection involves identifying patterns in data that don't conform to established norms. These patterns are termed anomalies, outliers, or exceptions. Within SASE environments, this approach leverages several methodologies to identify potential security incidents. Statistical methods analyze underlying data distributions to identify outliers using techniques like Z-score analysis, which are effective for data with clearly defined distributions but may struggle with complex patterns. Cluster-based methods group similar data points and flag those that deviate significantly from these clusters, making them particularly effective for multidimensional data where relationships between variables help identify outliers. Deep learning approaches utilize artificial neural networks to process large, complex data sets with high accuracy, though they require substantial computational resources. The implementation of behavioral analytics in SASE environments focuses on several critical anomaly types that indicate potential security threats. These include users accessing applications from unusual locations or at atypical times, access from multiple locations in time frames that suggest impossible travel connections, through anonymous proxies or from suspicious IP addresses, unusual file download or upload patterns, access to suspicious domains, and atypical application usage patterns that deviate from established baselines. For effective implementation, security experts recommend adopting hybrid detection methods that combine statistical, machine learning, and rule-based approaches to enhance accuracy. Adaptive baselining is particularly crucial as it establishes baselines that continuously evolve to account for legitimate variations in behavior patterns like seasonal trends or operational changes, minimizing false positives while maintaining detection capabilities. The integration of user and entity behavior analytics, or UEBA, functionality into SASE platforms addresses limitations in traditional security monitoring tools, which often lack comprehensive behavior-based anomaly detection capabilities. This integration is particularly valuable as enterprise systems become increasingly complex with distributed applications, multi-cloud deployments, and expanded attack surfaces that honestly render traditional monitoring approaches inadequate. Unified SASE solutions offer significant advantages for behavioral analytics by delivering consistent, comprehensive data across network and security functions within a cohesive architecture. This unified approach alleviates correlation challenges that arise when attempting to analyze disparate data from multiple vendors with varying log formats, schemas, and content completeness. By implementing feedback loops where security analysts validate identified anomalies and feed results back into detection models, organizations can continuously improve accuracy and reduce noise over time. This approach enables SASE platforms to adapt to evolving threat landscapes while maintaining high detection rates for sophisticated attacks that might otherwise evade traditional security measures. Network traffic pattern recognition is a crucial component of SASE security frameworks, enabling organizations to distinguish between normal and abnormal data flows across their networks. These patterns encompass the volume, direction, and frequency of data packets exchanged between devices, providing valuable insights into network utilization and potential security threats. At its core, effective traffic pattern recognition requires, establishing baseline behaviors to distinguish between normal and abnormal activities. Standard traffic patterns typically exhibit consistency in data flow during business hours, reflecting expected internal communications between servers and endpoints, as well as regular access to frequently used applications. In contrast, abnormal patterns manifest as sudden data transfer spikes, unusual outbound connections to unknown IPs, excessive repeated requests to single endpoints, or communication with command and control servers. The analysis process employs several sophisticated techniques. Application session inspection examines application-level data over network sessions, including duration, endpoints involved, and communication patterns, providing deeper visibility than traditional deep packet inspection. Also, machine learning models analyze network traffic in real time to detect behavior deviations from established norms, identifying suspicious anomalies like data exfiltration that rule-based methods might miss. Signature-based analysis searches for known attack patterns in traffic, enabling rapid detection of established threats. However, it's less effective against zero-day exploits. Tools like TP-Prof have emerged to automate this complex process, introducing novel abstractions such as network states, which capture approximate snapshots of link utilization and traffic pattern subsequences, representing finite state automata over network state sequences. These tools help extract meaningful patterns from the overwhelming volume of network data, making the process a lot more manageable for security teams. In SASE environments, network traffic pattern recognition is particularly valuable for detecting sophisticated threats that might otherwise go unnoticed. For instance, in all-to-all communication scenarios where multiple accelerators exchange data, ideal patterns would show uniform traffic distribution. However, real-world analysis often reveals burst patterns and spikes in sending rates that could indicate potential security issues. The integration of network traffic pattern recognition with other AI capabilities in SASE platforms creates a robust security posture. NTA solutions continuously analyze network telemetry and flow records using machine learning and behavioral analytics to establish baseline normal behavior. When irregular activities occur, these systems alert security teams to potential threats, providing extended visibility regardless of whether users are on premises, in the cloud, or working remotely. This comprehensive visibility extends from headquarters to branch offices, data centers, roaming users, and IoT devices, enabling organizations to attribute malicious behavior to specific IP addresses and perform forensic analysis to track lateral movement within the network. The result is, faster threat response and mitigation, preventing business impact before significant damage occurs. Shadow IT detection has become increasingly critical in SASE environments as organizations face the growing challenge of unauthorized technology usage, especially with the emergence of shadow AI. Unlike traditional shadow IT, which involves unsanctioned hardware or software, shadow AI represents a more sophisticated threat through the unauthorized use of AI applications that often operate stealthily within browser extensions or AI-enabled SaaS tools. Most large organizations honestly vastly underestimate the number of applications in use by employees, resulting in significant blind spots in compliance and security. This problem has really intensified with the rapid adoption of generative AI tools, where employees frequently input sensitive data into personal AI tools without understanding the associated risks. So, shadow AI introduces several critical security threats that organizations really need to be aware of. First, there's improper data handling, where employees might upload proprietary or confidential information into public AI models without any IT oversight. Then you have compliance violations, which can happen when regulated data is processed through unauthorized AI channels. Prompt exposure is another big concern, since it could reveal sensitive business strategies or even intellectual property. There's also the risk of data leakage through AI tools that may store or repurpose enterprise information. And finally, there's a lack of auditability over how data is stored, used, or trained upon by third-party AI providers. Now, effective shadow IT detection in SASE frameworks relies on several advanced techniques. SaaS risk assessments really serve as the foundation for detecting shadow technologies by scanning the environment for misconfigurations, excessive permissions, and unauthorized data sharing. These assessments help identify which applications have access to sensitive data and evaluate the security posture of AI integrations. AI-specific monitoring tools provide, specialized capabilities to detect unauthorized AI usage. For example, Cato Networks' KSB feature includes a shadow AI dashboard that offers user-level visibility into Gen AI tool usage across browsers, APIs, and embedded applications. This system can automatically detect and categorize both known and emerging Gen AI tools, and it does so with built-in risk scoring. Unified SASE platforms deliver comprehensive visibility by converging networking and security functions. This integration enables organizations to monitor all traffic, users, and applications from a centralized view, ensuring consistent policy enforcement across remote users, branches, and cloud environments. The unified approach alleviates correlation challenges that arise when analyzing disparate data from multiple vendors. AI-aware data loss prevention, or DLP, utilizes machine learning-based classifiers to inspect data shared with AI applications, thereby preventing the exposure of sensitive information. These systems can enforce granular security policies across all network traffic, blocking data uploads to unapproved AI tools based on user, device, or application context. 2. Effectively manage shadow technologies. Organizations should implement a multi-layered approach. First, establish clear governance policies outlining acceptable AI tools and usage guidelines. Next, promote transparency by encouraging open communication about AI usage. Then, deploy shadow IT discovery solutions to identify unauthorized applications. And finally, implement continuous monitoring to detect new shadow technologies as they emerge. By integrating these detection capabilities into their SASE frameworks, organizations can strike a balance between innovation and risk management, enabling employees to leverage beneficial AI technologies while maintaining appropriate security controls. This approach transforms a potentially chaotic AI landscape into a managed, secure ecosystem that supports rather than hinders business objectives.